Hey guys, this is lecture video 10 of CSE2000Q2S Computer Science 2, taught by Lawrence Orijuela, and my name is Lawrence Orijuela. Today is November 6, 2020, and we will be discussing recursion. So if you look at our tentative schedule, we are proceeding as planned. Today is November 6th, we're discussing recursion. And you have one item due, well, not tonight, but the item that's due is your activity 6. And if you saw the emails, you'll see that I pushed the due dates for activity 8 from November 6th to November 8th, just to account for me being late those 2 days. But if you can get activity 8 to me before midnight of November 6th, I'll give you bonus points. But you can still turn it in by November 8th. Okay, so moving forward, there's a couple things we need to discuss. First and foremost, so the last 4 weeks we were discussing about classes, inheritance, and overloading. This was actually the most difficult part of the class, but we are in week 11 right now, and we are officially done with classes. So the hardest part of this course is officially over. So congratulations for that. And so if you finish your lecture activity 8, the very next thing you should do is that you have everything you need in order to complete your lab 3, the school database. And I made a very short 20-minute video showing how to finish lab 3, assuming you've already finished lecture activity 6 through 8. The link is on Blackboard, but the link is also here too. So please make sure you watch this video so you know how to do everything. And please get lab 3 to me before the due date, okay? And just as a friendly reminder, here are the Zoom meetings that are remaining for the rest of the semester. So once again, on November 13th is the Zoom meeting for lab 3, because lab 3 is going to be due a week from that day. So lab 3 will be due on November 20th. And this is the Zoom meeting that you need to attend just in case your personstype.h, studenttype.h, or your faculty.h has errors. Please use this meeting to consult with me, and we will work together and resolve your errors. Okay? And then, so this Zoom meeting is going to be on November the 13th. And then the other Zoom meeting is going to be on December 4th. And it's going to be a Zoom meeting in regards to the final exam. I will be posting the final exam on Blackboard sometime in the future. And for the final exam, it's going to be the same deal with the midterm. There's going to be 5 problems. 5 coding problems, okay? Your best 4 problems will be graded. Your worst one will be dropped. And just like the midterm, we will use this Zoom meeting for you to decide as a class which question on the final is the hardest. And once again, we will do the hardest question as a class together. And then, in case you haven't seen it already, your practice final has already been posted on Blackboard. And I lumped this Zoom meeting together with the meeting for Lab 4. But funny note about that, I did a little bit of thinking, since we are winding down to the end of the semester. So we only have 2 things left to discuss. We're going to take 1 week to discuss recursion, which is now, and then we're going to take 2 weeks to discuss searching and sorting. Okay? But since we're winding down, I did think about a couple things. So here are my other thoughts. One, I'm thinking of possibly throwing out Lab 4, because I was looking at the course material that I made for this class, and I realized that the material for Act 10 and Lab 4 are too similar to each other. So I kind of don't see the point in making you do the same work twice. So this is just a thought of mine. I'm thinking of just discarding Lab 4 entirely and just giving each student 100% on Lab 4 in their grades. I don't think anyone will object to that. But that's just something that came to mind. And the other thought that was in my mind is so the truth is, your final exam, I already wrote it. It's already ready to be distributed. I said before that I would post it on November 27th, but the truth is, if it's a take-home final, and if it's ready to be distributed now, I don't see any issue with just putting the final exam right now on Blackboard, and then you have the remainder of the semester to turn it in and get it to me before December 11th. So I just have these two thoughts in mind, because I was thinking maybe if you get the coursework for this class out of the way, you would have more time to focus on the coursework for your other classes. But I don't know. It's just a thought of mine. I'm gonna consider it more and more as we're moving forward. But anyways, recursion. So recursion is a very brief subject. I imagine that this is going to be a very short video. Okay, so let's get down to it. So recursion. Recursion is the process of solving a problem by reducing it to smaller versions of itself. Recursion is a very powerful way to solve certain problems for which the solution would be otherwise very complicated. Okay. Now, when it comes to programming, recursion is usually performed through a function, a user-defined function that calls itself in the definition. Yes, you can do that. Is considered a recursive function. Okay. So, to write recursive functions, one must try to create a recursive definition. And a recursive definition consists of two parts. One part is the base case. This is the case in which a solution can be obtained directly. In other words, there's no recursion or recursive calls that is being made anymore in order to reach the solution. The other part is the general case. This is the part of the definition where recursion is required, where the function calls itself. Okay? So the general format for recursive functions is here. There's no syntax or anything because I wouldn't call this syntax because when it comes to recursion, there's many ways you can do it, but the general idea is that you have an if statement. Inside of the parentheses is a condition in which an answer is known. In other words, it's the base case. And then you simply enact the lines of code in which the solution is obtained without recursion. And if this condition is false, we use the recursive call to further break down this problem into its constituent steps. Okay, so a lot of times when professors teach recursion, a classic example that they use is factorial. In mathematics, right? So you know how factorial works. So 1 factorial equals 1. 2 factorial equals 1 times 2. 3 factorial equals 1 times 2 times 3. So n factorial equals 1 times 2 times 3 ... all the way to n. Okay? So we get 1 factorial equals 1. 2 factorial equals 2. 3 factorial equals 6. So on and so forth. So you get the picture, right? Well, if you reach this level in your coursework, of course you've seen factorial already. But in mathematics, the formal definition of factorial in the case of non-negative numbers, is defined with these two stipulations. So 0 factorial equals 1, and n factorial equals n times n minus 1 factorial. And looking at this, I can see that I made an error in this PowerPoint. I should actually have an exclamation point here. So let me fix that right now. There we go. But anyways, yeah, so this is a very easy example in which I can introduce recursion to you. Okay? So if I wanted to create a recursion function that returns where it takes an int n and it returns the factorial for that number n, I can do that using a recursive call. So this if statement here with the solution statement, this is the area where I would put the base case, and in the else, this is the area where I would put the general case. Okay, so I can introduce this to you if we do the first part of the lecture activity now. So lecture activity 9 part A, this is one example of recursion, the factorial function. So write a recursive user-defined function of type int called factorial that accepts an integer n and returns a factorial of n. Okay, this is going to be very, very simple. So let's get out of here. Open Visual Studio. Okay, create new project. Save this where you would normally save it. Yeah. Oh, not there. I'm trying to save it. Yeah. Okay, so this is going to be very, very easy. So let's add our main.cpp. Okay, so as stated earlier, recursion is usually done through user-defined functions. So as we were saying before, this is going to be a recursive user-defined function of type int called factorial and accepts an integer n. So we're going to say int factorial is going to accept an int, which we're going to call n, okay? And then we have to put the prototype up top, right there, and delete this name. Okay, so as mentioned before, the general format for recursive functions is shaped like this. So we only need one single if-else statement. The if statement is going to include the base case. The else statement is going to include the recursive function call. Okay? So let's go back. So we're going to have an if statement here, okay? So the condition of the base case is if our n equals 0. If n equals 0, we will return -1. Okay? That's easy enough. So if n equals 0, I'm using my comparison operator here. So if n equals 0, the code that's concerned with the base case will occur. But if it's not 0, we will do the recursive call. So in other words, we will do else. This is the area where we do the general case. So if n does not equal 0, we will return n times the factorial of n minus 1, okay? So, in the situation of the base case, we know what we're doing. We have to return 1. And in the situation with the general case, we will return n times the factorial of n minus 1. So factorial n minus 1, like that. And that's it. So I want you to take a moment to like really look at how this function's occurring. So if you tried to make a user-defined function that returns the factorial of an int n without using a recursion, it would be very hard, right? Because let's say n equals 7, right? So you would have to continuously take 7, multiply that by n minus 1, which is 6, and then do it again, n minus 1, which is 5, then 4, then 3, then 2, then 1, right? But by using recursion, we actually made the problem of calculating a factorial much simpler by actually breaking it down into its constituent parts, okay? So the first thing we had to do was take 7. And then, as you can see, this user-defined function factorial, it calls itself. But instead of taking 7, it returns 6 now. So as a result, what happens is that let's say the n was 7, right? So 7 factorial of n minus 1, which is 6. Like, I guess it would be worth it to write a bunch of comments here. So let's actually do it like this. So we had, when it calls itself the first time, we're going to get 7 times factorial of 6. Oh. I don't know why it's doing that. There we go. Of 6. And then when factorial 6 is counted, it's actually going to calculate 7 times 6. And then when it does the recursive call again, because 6 does not equal 0, this else statement will occur. We're going to get 7 times 6 times 5 times factorial n minus 1, which is going to be 4, right? And this would actually keep continuing until we get down to 7 times 6 times 5 times 4 times 3 times 2 times factorial of 1. Well, actually, factorial 1 times factorial of 0. Now, what happens as a result of this occurring is that eventually, as it's continuously calling itself, eventually factorial, the n will eventually equal 0. And when n equals 0, this else statement wouldn't occur anymore. Because n equals 0, we would return the base case. So factorial of 0 would end up being 1. And as a result, we would get whatever the factorial of the number we put in is. Okay? Now, this would make better sense if I actually use this function right now and you saw me debug this. Okay? So I will call the function here. I will say cout factorial Factorial 7, like that. And if you watch me debug, you will actually see what's happening here. So I'll put a breakpoint here, and let's start this. Okay, I'll put this here, this here. So when factorial is called, the n that's being passed to it is 7. So if I step, the compiler will jump here. So the first thing it'll do, it'll check if 7 is equal to 0. Because that's not true, it's going to commit this else instead, which it does. So in the first call of factorial, it's going to return 7 times whatever this will return. So we're going to say factorial 6, okay? So immediately the pointer jumps back to factorial, okay? Now this time, the n that's being passed to it, if you look here in autos, the n that's being passed is 6. Because 6 doesn't equal 0, it'll jump down here again. So it'll return 7 times 6 times factorial 5, okay? It'll jump back to the definition of factorial. Because 5 doesn't equal 0, it'll do it again. And then 4, and then 3, and then 2, 1. Now we're at 0, right? Because 0 equals 0, we will return the base case. So because of this, the correct way of thinking about this is to imagine 7 different factorial functions being nested into each other. And then after n equals 0, the 7th factorial function returns, which means the 6th one can return, then the 5th one, then the 4th, and it's kind of like dominoes. It's once the base case is reached, all of the nested factorial functions will collapse back in on itself, and it will retrieve the solution that we're looking for. So as a result, we should get whatever the factorial of 7 is. So it's returning, see? And it has to return like 6 different times, I believe. Yeah. So now we go back here to line 9, because the factorial 7 finally returned. And what we see as a result is this number, 5040, which I believe is the factorial of 7, right? 7 times 6 times 5 times 4 times 3 times 2 times 1. Yep. So this is 5040 is the factorial of 7. Now, can you imagine trying to write a factorial function without using recursion? In other words, having it so that the function doesn't call itself. That would be pretty hard, right? So recursion is, you're going to see recursion a lot, especially when you go to higher division computer science courses. And it's going to be very useful for solving problems that you think that it would be very difficult to find solutions for. So this is a very classic cut and dry example of factorial. So here's what I'm going to do now. We should break this into sections like the same way that we've been doing it normally. So here's what I'm going to do. Let's remove this breakpoint. So this is lecture activity part 9A. Okay? So I'm going to go here. This is part A. One example of recursion factorial. And I guess to demonstrate this working, here's what I'm actually going to do. I'm going to take this, copy it a whole bunch of times. Let's start from 0. 1, 2, 3, 4. And then we can actually see the factorials of 0, 1, 2, 3, and 4 if we ran this again. Yeah, these look right to me. So 0 factorial is 1, 1 factorial is 1, 1 times 2 is 2, 1 times 2 times 3 is 6, times 4 is going to be 24. So yeah, this factorial function works correctly. So I'm going to give myself a little room and the line there. Okay, so this is part 1 done. Cool. So moving on. So all of this I mentioned already, but here's actually another example of recursion. So another example is Fibonacci numbers. So you've probably seen this before in your math class, right? Or somewhere else before, but the Fibonacci number sequence is a sequence of numbers where the next number in the sequence is going to be the previous two numbers added together. So, well, starting with 0 and 1, of course. So, if the first term is, if the 0th term is 0 and the first term is 1, the term after that is going to be 0 plus 1, which is going to be 1. And the next term after that is going to be 1 plus 1, which is going to be 2. And then 1 plus 2 equals 3. Then 2 plus 3 equals 5. 3 plus 5 equals 8, and so on. Okay? So in mathematics, the definition of I guess the definition of factorial numbers, Fibonacci numbers, is where we have two base cases where the 0th term is 0 and the first term is 1, and then the nth term is going to be the n minus 1 term and the n minus 2 term. So the previous two terms together. So these two statements are the base case. And this is going to be the general case. And that's what we're going to use to build the recursive function to output Fibonacci numbers, okay? Oh. So this is lecture activity 9, part B, actually. And we are going to write a recursive user-defined function of type int called Fibonacci that accepts an integer n and returns the nth Fibonacci number. So this is going to be also very easy. So when you're creating your own recursive functions, well, that is if recursion can apply to the problem which you're trying to solve. The general idea that you have to keep in mind is that you have an exit condition, which is your base case, and then you have your recursive call. Okay, so if you remember this format, you can use recursion on anything. Okay, so yeah, here's what we're trying to do. So let's go back. This is part B. Another example of recursion. Fibonacci. Yeah. You're going to use recursion many times as you progress in the computer science field. So what we need to do is make a new user-defined function called Fibonacci. Okay, so I'm going to go to the bottom. There's going to be of type int, of course. And it's going to accept an int n. We'll take this, put it over here, because this is a function prototype, add a semicolon, delete the name. Now, when I was planning this course, I was actually kind of considering having user-defined functions and recursion be in consecutive weeks, but I tried to make it work since they're closely related to each other. But I decided to move recursion over here instead because it's one of those out there subjects of C++. But anyways, so this is going to be very simple. We are going to use the general syntax, general format again. So if our n equals 0 or equals 1, if it's 0, we will return 0. If it's 1, equals 1. So if that's the case, if it's 0 or 1, it'll return itself. That's the correct way to think about it. And then in the recursive call, we will return Fibonacci minus 1 and Fibonacci minus 2. So going back, we'll have if n, well, there's two scenarios, right? If n equals 0 and, well, or, right? Or, so as you learned in operator overloading, the double bar means or n equals 1, right? So if n equals 0 or n equals 1, this is going to be the base case. But if this turns out to be not true, this is going to be the general case, or the recursive call, okay? So this is going to be very simple. So if n equals 0 or n equals 1, in the case of in which is 0, we'll return 0, but if it's 1, we'll return 1. So it looks like we're going to return n, right? Yeah, because I think about it, if n equals 0, we want it to return 0. So if this is the case, we'll return 0, and but it's 1, we will return 1, right? So that was easy. The part that might be trickier for you is doing the general case. So what we have to do in the general case is that we have to return the Fibonacci of n minus 1 and n minus 2. So return n minus 1 plus n minus 2. And this makes sense because the next number in the Fibonacci sequence is going to be the previous term plus the term before it, right? Because that's what we've been doing, because 8 is going to be 3 plus 5, and then 5 is going to be 3 plus 2. You get the logic, right? So if we did this, we can, if we enter n, we can retrieve the nth Fibonacci number. And we can demonstrate that here if I call the function. So cout let's say I wanted to know the fifth Fibonacci number, right? Now, according to this PowerPoint, the fifth number is going to be 3. So let's see if that's the case. It didn't. Hold on. Let me see. Try that again. What'd I do wrong? Oh, my bad. This returns 0. It has to be down here. Yeah, that's my mistake. So let's try this again. This should return 3. Or 5. So the fifth Fibonacci number is going to be... Okay, so this is 0, 1, 2, 3, 4, 5. Okay, so it is working, okay? So if you want to see me debug this again, I'm going to put a breakpoint here. And you can watch it. So I'll put this here, this here. So now, the weird thing about this function is that it's calling itself twice. But that's okay, right? It can call itself as many times as it wants because each time n is decrementing, right? Eventually, n is going to be equal to 0. And that's when the nested Fibonacci functions, they're going to return, and it collapses in on itself, and it returns the answer in which we want, right? So I'm going to step through this because 5 is not 0 and 5 is not 1. This is going to occur. So what happens is we get Fibonacci 4 and Fibonacci 3. Fibonacci 3 is going to be calculated first, right? So it'll continue calling itself, but eventually it'll return. Just like that. And eventually, we will go back to line 35. And then we see out 5, okay? So, as we can see, this is working. And I'm going to do this the same way we've been doing it before. I'll take this. And just to illustrate to you that this is working as planned, I'm going to start with 0. 1, 2, 3, 4. So it looks like this function is working as it's intended. 0, 1, 1, 2, 3. The next one would be 5, right? Yep. And then the one after that would be 8, if I change it to a 6. Yeah. It's working the way it's supposed to. Okay? So, that was actually it for recursion. So, recursion is very simple, right? And if you know how to use it properly, it's super, super powerful. So, we are actually done with this lecture activity. So go up here, go to the top. You know what to do. This is going to be due on the 13th, 2020. Okay. So run this once more. Well, actually, first, I'm going to zoom out so you can get everything in case there's anything that you missed. Okay. And then run it once more. Take a screenshot. Email this to me. And then attach the CPP file. Okay, so this is actually a very short lecture today, but we actually covered everything that I wanted to show you in regards to recursion. So, yeah, if you haven't already, what I'd like you to do is if you haven't already, go watch the video showing you to how to assemble lab 3, and I can actually pull it up on my other monitor here. If I can, yeah, this video here. So if you go to this video, this will show you how to do lab 3, and it's very simple. So make sure you do that and get it to me before the due date. But anyways, that's it for this video. I will consider more about these two things that I mentioned here. But for now, that is it. And next week, we will take 2 weeks to discuss searching and sorting. So I will see you later.